Hi and welcome to Chemistry 30 with Miss Verity. Today we're going to be looking at the equilibrium constant. So the mathematical relationship that exists once equilibrium is reached between the products and the reactants is represented by the following. So for the reaction, A plus B produces C plus D. So our K and Q expression is equal to, I would say, the concentration of the products over the concentration of the reactants raised to the power of their coefficients. So specifically for this equation, our KQ expression would be equal to, so products, we've got the concentration of D raised to the power of D times the concentration of C raised to the power of C all over the concentration of B raised to the power of B times the concentration of A raised to the power of A. So whatever your element is raised to the power of the coefficient from the balanced equation. So that's where all those powers came from, was the coefficients from the balanced equation. So KQ has no units and is a constant for any particular reaction. Its value doesn't change unless temperature does. So that's the only time, when the temperature changes. It does not depend on the initial concentrations used to reach the point of equilibrium. So concentrations of both aqueous and gases change during the progression of a reaction. Reactions involving solids and liquids, while their amounts change, their concentrations do not. And so that's similar to where we talked about in Le Chatelier's principle with our concentrations, how it was only gases and aqueous things that affected it. That's because solids and liquids, their concentrations are always at 100%. You can have larger or smaller amounts, but no matter what, that concentration will always be 100%. So as a result, solids and liquids are not included in the equilibrium constant expression. So example 1, write the equilibrium constant expression for the following reaction. So things we want to take note of, first and foremost, is we want to look at the states. Second thing, we'd want to double check that it's already balanced for us, and yes, in this case it is. So our KEQ is equal to our products. Well, notice our product is a solid. Therefore, we can't include it in our KEQ expression. Well, if we can't write anything into our KEQ expression, we're just going to write a 1. There's nothing there, we're going to have a 1. So then over our reactants, well, in this case, we've got CO2 raised to the power of 1. You don't have to write the 1. I'm just doing that for emphasis in this case. And if we look at our calcium oxide, that is a solid, meaning we're not going to include it. So that would be our final KEQ expression. If I was to actually write it, it would just look like this. Again, all the square brackets mean is concentration. So whatever the molarity is of those compounds. For the equilibrium system described by 2SO2 plus O2 produces 2SO3 at a particular temperature, the equilibrium concentrations of SO2 and O2 and SO3 were 0.75, 0.3, and 0.15 molar respectively. At the temperature of the equilibrium mixture, calculate the equilibrium constant KEQ for the reaction. So some important things to note is that in order to put things into our KEQ expression, they have to be at equilibrium, which in this case, it told us that it was the equilibrium concentrations. So we're good. So our first step, which on a test, quiz, whatever, that's worth a mark, is writing your KEQ expression. So again, products, we've got our concentration of SO3. It is going to be squared all over, we've got our O 2 to the power of 1, which I'm not going to write because science people are also lazy, SO2 squared. So that's our KQ expression. So now to figure out what the equilibrium constant is equal to, we are going to plug in our known values and solve for KQ. So our concentration of SO3 is 0.15. Our concentration of O2 is 0.30. And our concentration of SO2 is 0.75, and that is also squared. So, oops, and I forgot my squared in my numerator. So, type that into your calculator. 0.15 squared is 0.0225 over, we've got 0.3 times 0.75 squared. So that's 0.16875. 0.0225 divided by that gives us a KEQ equal to 0.133. Just like in physical science, important things is we need sig figs. So in our question, all of our numbers we were given had 2 sig figs. 1, 2, do we need to round? No, we don't. So KEQ is equal to 0.13. And remembering that KQ does not have any units, so that is our final answer. So our next example is for the equilibrium system described by PCl5 produces PCl3 plus Cl2. KQ equals 35 at 487 degrees Celsius. The concentrations of PCl5 and PCl3 are that respectively. What is the concentration of Cl2? So again, first step, we are going to have our KEQ expression. So we've got our products over our reactants, PCl5, and we're going to plug in what we know. So we know that our KEQ is equal to 35. Our concentration of Cl2 is what we are looking for. Our concentration of PCl3 is 0.78. And our concentration of PCl5 is 0.015. You don't have to use square brackets. You can use round brackets. It's fine. Okay, so how do we solve? Personally, in this case, I would multiply both sides by 0.015. So that's going to reduce to be 1, and I've got 35 times 0.015. So 0.525 is equal to Cl2 times 0.78. So now divide both sides by 0.78. And we get 0.67308 is equal to the concentration of Cl2. Again, we need sig figs. In this case, everyone had 2 sig figs. So 1, 2, do we need to round? Nope. 0.67. Our units for concentration are molarity or moles per liter, so that's going to be equal to our concentration of Cl2. So lastly, for a very large KEQ, the concentration of the products is much, we're running out of room, I lost all, much greater than the reactants. We'll try that again on this line. The reaction essentially goes to completion. That means the forward reaction is actually happening. If we have a very small KEQ, so the concentration of the reactants is much greater than the concentration of the products. So this means the reaction does not occur to any great extent. So most of the reactants remain unchanged. And very few products. So if we have a KEQ close to 1, you're going to have roughly equal amounts of reactants and products. All right, have fun doing some practice.